Okay, so it's a pleasure to introduce Aaron, who'll be speaking on Shtukas and global Langlands for function fields.
So thank you so much. I just want to give a major thank you to Professor Drinfeld because about 2 weeks ago when I started, or a week and a half ago when I started learning this, I did not know what a Shtuka was. And so I had started really from nil. My knowledge had no legs. And now, thanks to his very patient and very determined tutelage, I have some understanding of this. So I hope that's not, I hope that could be either an advertisement for this talk or an anti-advertisement, a very inexperienced speaker who was tutored by the best. So, let's hope that Drinfeld's influence wins out over my ignorance. So he really spent a great deal of time teaching me some really wonderful and amazing things. So my hope is to actually outline von Lafforgue's proof of global Langlands for function fields. And so we're going to begin with a review of global Langlands, and hopefully at the end I'll also be able to explain Drinfeld's reinterpretation of some of the structures that occurred, as that directly related into the AGKRRV work, which is the subject of this quarter's seminar. So without further ado, let's introduce some notations. Let start with G, a reductive group. Now, the whole purpose of this of von Lafforgue's work is that it's an arbitrary reductive group, but in order to simplify notation, I'm going to assume it's semi-simple. The only difference between this and the general case is The only difference between this and the general case is you'll see a lot of mod capital X's in von Lafforgue's paper, and that's entirely for this reason, that when you have a center of G, you need to mod out by a cofinite lattice. So to get rid of having to write that over and over again, I'm just going to assume G is semi-simple and the full force will still go through. So let X be a smooth, projective, geometrically connected curve over FQ. If we have V will be used often to represent a place of X, then we have the associated rings OV, which is going to be the formal completion. Formal disk at V, and FV is the punctured disk. So spectrum of OV is this, and spec of FV is the punctured disk, and FB is the fraction field of OV. Make sure that I'm not missing out anything, because if you forget some notation at the beginning, I don't want to have to introduce it later. So let's see if we're good. Yes. Eta. So F without any subscript will denote the function field of X, and eta, which is spec F, will be the generic point, and we're going to choose once and for all point of X. We're going to choose once and for all a geometric point factoring through eta, so pick an algebraic closure. So my first job is to state the global Langlands correspondences. So for this, we need, I'm firstly going to mention a couple of simplifications from the outset. For us, again, this is essentially notational. I'm going to take the unramified case. Von Lafforgue's argument goes through what's again just extra notation. You need to put a subscript n everywhere for the level structure. So this doesn't actually come at that great cost to the argument. And I'm going to introduce a couple of things so I don't keep having to write the double quotient. So we're going to freely use the fact that we've discussed many times that BunG, Bun sub G, x fq is equal to gf mod ga mod. So we might actually obviously split in this case. Again, at little extra cost to the whole argument here. And we're also going to use some general facts about cohomology. Is just the absolute Galois group. I1 of the curve itself is the unramified maximal extension. We insist that it's unramified over all places B. All right, so now for the first important definition. A global Langlands parameter sigma is a homomorphism, right? It's actually a conjugacy class of homomorphisms from the absolute Galois group of F to the QL bar points of the dual group. And we're going to insist on a couple of extra bits of data. It must be continuous. It must factor through some finite extension E of Q of QL. It must be, this is the most interesting, semi-simple. That is to say that if the image of sigma is contained in some parabolic P in the dual group, then the image is contained in some Levi factor.
Sorry, Aaron?
Yes. Yes.
Is your group split?
Yes, for us, we're going to just make the group split as a simplifying assumption, so we don't have to add over all the kernel H1 Galois constants. I should probably say for a single split. Yeah. And let me just make sure that I'm not missing out anything else. Oh yes, and it factors through I1, it's called U for some Zariski open U. Make my handwriting has got a little bit smaller, so I'll make it big again. Contained in X. All right, so that is the data of global Langlands parameter for us. Now, there are some extra things, there are extra properties of this Langlands parameter, which we should mention. We should say it is cuspidal, and then unramified. If the image of sigma is not contained in any proper parabolic subgroup. So that is to say, the only parabolic subgroup of G hat that it actually is contained is G hat itself. So it doesn't factor through some smaller reductive, which would mean it's sort of induced. And we're going to say it's unramified. Unramified if all right, so for all B in X, well, so there's a very fast way of saying it, which is it factors through I1 et al. X. So the full curve. But I'm going to give a little bit extra, on this. If for all B places of X, we have the map not going to quite be able to fit this on one board, given my size of my handwriting, so I'll just go on to the next board. No need to be sentimental about space when one has a classroom this big. If for all V and X, the absolute Galois group of FV over F, which embeds not canonically but up to conjugacy in the global Galois group, is composed with sigma to get into the P hat, factors through the Galois group of the residue extension, like this. And in this circumstance, when we have an unramified place for a given Langlands parameter, then we can talk about sigma prob V. Oh, thank you. Sigma prob V, which is again a well-defined up to conjugacy in QL bar. So those are the one side of our that we're going to be using to parameterize our correspondence. So now we go from the Galois side to the automorphic side. We'll consider the decomposition of. So now I'm going to say about this quickly. Another simplifying assumption, which I haven't written here, is not on G, but it's on the aspect of the Langlands correspondence that we'll consider. We're only going to be considering the cuspidal unramified setting for this, again, to save notation. And also, in this case, to save notation for the unramified one, but the cuspidal one, because that's actually what ensemble proves. The rest of the Langlands correspondences come from general properties of induction. Once you prove it for cuspidal, it applies it for general reasons for all cases, but it requires some extra analytic considerations like non-compactly supported functions on BunG that I don't want to get into for this talk. So we're going to consider C cusp of BunG XFQ. Again, we're thinking of this as adelic double quotient with coefficients in QL bar. And so this is going to match with because we're picking BunG and not BunG with a level structure, this is going to match with the unramified case, and we're going to, the cuspidal will match with the cuspidal. And we're going to consider the decomposition of this space. And yeah, so I want to define now what functions are cuspidal. So which is so we'll consider the F. So okay, so I'll say F in the compactly supported functions on BunG, FQ is cuspidal if for all proper parabolics E contained in G hat in G in this case. We're on the automorphic side, so the G function hat. The constant term functor given by BunG, BunP, other FQ, mapping to BunG, FQ, mapping to BunM, FQ for Emma Levi. We have these maps we're going to call P and Q by convention, which is the functor Q lower Schweik, P upper star. So pushing functions from BunG to BunM is equal to 0. Recall that in the function setting, lower Schweik corresponds to just integrating, and because of our simplifying ideas, and because we're working only in compactly supported functions, all of this just amounts to a finite sum. So this is a very readily verifiable condition for all P. Okay, so
true. I don't know if you know, like if hospital implies compactly supported, if I don't know that.
I think hospital probably, I actually don't know. I think in order to get the non-ramified, the non-hospital setting, I couldn't do compactly supported. Those Hecke eigenfunctions are not compactly supported, but I didn't think about whether immediately that particular solving of all these linear equations will inflict the compactly supported. It's possible. It's possible.
The corresponding thing is true in the sheet.
Oh, then probably it is. No, certainly it is true. Yeah, that's a good question. I didn't know that. One of the things Mr. Drinfeld told me that would be great is if someone asked me a difficult question, I don't know. He said that if we were speaking, it's embarrassing to so I will plead ignorance on a good number of questions, but this I think yeah, you're probably right. Okay, so where are we now? We're at the point where we're going to now, yeah, we're going to have now. In order to, what we're going to do is we're going to be decomposing the space of functions on BunG X that are customary. That is the content of the language. But of course, that's totally vacuous unless we have something to constrain this this phenomenon. That is the Hecke compatibility. So I'm going to very briefly say all HV is GOV mod GFV mod GOV. Okay, sorry, as C actually supported infinity functions on this double quotient space. These form an algebra under convolution. And the content of the Satake, classical Satake isomorphism, is that, and again, I should say this is for a specific, place B. Satake isomorphism is that for all places B, HV is isomorphic to the category of representations, Roten category of representation, tensor category of the Grothendieck ring. Yes, Grothendieck ring. Yes, so I should probably put K0, right? Sorry, my notes may be actually, yes. So in particular, the inverse Hecke correspondence, which I might just call the Hecke correspondence, associates to every reducible representation, every representation in there, a corresponding Hecke operator, let's call it W to make it. A corresponding Hecke operator TW with respect to the place. Okay, so that's all we need for this. Now we can state the it doesn't. It's place independent, but you see what the Langlands correspondence does is it says that as we vary the V's, the sort of data coming from the same W here will vary exactly as Frobenius does inside of this Langlands parameter. So that is the thing that makes the Langlands correspondence actually interesting. Is the force of varying the V's. So we'll get to that in a second. So okay, so and then we're at okay time. This asserts that CC hospital of BunG FQ. Again, everything has coefficients and functions valued in QL bar is equal to the direct sum over sigma Langlands per cuspidal unramified. I'm just going to say sigma and then cuspidal unramified Langlands parameters of these spaces, which we're going to call my effort on board fracture capital H sigma. It really does look like that when you see them in Lafforgue's writing, so I'm not too upset about this. Now, again, that says nothing. That's essentially back to this. So the constraint is Hecke compatibility. And so what is the constraint? Such that, okay, so I'm going to just say verbally, because I don't want to have to write down too much. Note that the Hecke algebra at any place can be embedded into global Hecke algebra, and therefore it acts on the adelic double quotient on the right. Okay, so each local Hecke algebra has an action on BunG Q with values in QL bar. So I'm going to talk about this action now, such that for all places B, and for all F in H sigma. Now this is an automorphic form, so we can act on it by the Hecke algebra corresponding to an all W in rep QL. I guess this doesn't matter if I say Hecke category or not. The hat T WV acting on F is equal to, okay, so we're going to take the Langlands parameter sigma, which has to get involved here, apply it to the Frobenius at B. Since everything's unramified, I would otherwise have to say only for the unramified B, which is almost all places B, times let's see. No, sorry, yes, now I need to say trace. So this is an operator now of the dual group, and this, of course, comes from a representation W. So this is actually the trace with respect to W of this operator. And this is just a scalar times X. Okay, so my beautiful original work has become trash. There we go. But yes. So that right there is the constraint. This is called Hecke compatibility. So now the reason I went through this all in detail is that the following is actually a serious problem. This is not enough to uniquely constrain Langlands correspondences. And at least according to Professor Drinfeld, in the number field case, Langlands correspondences are still underdetermined. For GLN, it will actually turn out that if you imagine some decomposition that satisfies this property, then it's uniquely determined. But for arbitrary G, reductive G, this is no longer the case. And this is due to the following reason. That I can have a map from gamma, which is going to be my Galois group, to some reductive group G, which is the dual of the Langlands group of G in this case, but I'm not going to put cat. And I can have two distinct maps from gamma to G that are not conjugate, but when I compose with G mod mod G, the map, the standard projection of G mod mod G, these can equalize. So I can have things that are pointwise conjugate, but not conjugate for all values of gamma. So Hecke compatibility is insufficient to constrain Langlands correspondence uniqueness. It does not have a multiplicity one phenomenon in which you can say, well, so it works. We test the Frobenius, and therefore we've discovered the Langlands correspondence for this. There might be more than one. So the Langlands conjectures themselves are underdetermined in this case. They are not visually determined. Now, the way that Lafforgue gets around this, and thereby says you can solve the Langlands conjecture, of course, conjecture for arbitrary G in the function field setting, is he considers a much larger algebra in the Hecke algebra, which acts on cuspidal automorphic space. And that is called the algebra of excursion operators. And the whole purpose of his 200-page paper and all the summary notes, which are very useful when we read this stuff, is to set up this algebra of excursion operators. And with the algebra of excursion operators, there's an enhanced version of Hecke compatibility. And that does uniquely specify responses. Now, unfortunately, the way in which the excursion operators are defined critically involves the fusion of legs of Shtukas. And we'll see this. It involves basically considering, in some sense, higher powers like this. I'll explain why. Now, the critical process of defining these operators involves the classic thing of taking two legs, separating these, or considering what happens when they merge. And this is the reason you can't do this in the number field setting, is for the classic reason that our curve X is supposed to look like Z. But we can't really talk about something like Z tensor Z if that's two-dimensional without, some sort of weird gadget like F1 that will allow us to basically perform fusion on the prime numbers. So this right here is why is the obstacle to defining excursion operators in the number field setting. And so far as Professor Drinfeld said to me, and this I can explain to experts, it seems that the Langlands conjectures in general for arbitrary G in the number field setting are still undetermined. We don't know. There should be a canonical correspondence, but we don't know what the extra conditions are. So in the absence of excursion operators, we might not have something. So any questions?
So there's this recent work by Farg and Schultz, right, which is supposed to kind of give sort of head it down in a local case. I don't know what you would imagine, but
That's amazing. So no, that's great. That also, yeah. I guess I did have again plead ignorance on this.
and it doesn't allow you to do this kind of thing. Having some sense,
This is on the curve.
that's what these perfectoid
Yeah.
things are supposed to.
But you can't, that's not going to work globally though, will it? Because this
No,
is
it's definitely a local thing, but then
Yeah.
you can hope that
Oh, I see. So you're saying, oh, it's going to correspond.
But
Okay.
it's then local.
Okay, so maybe, yeah, so maybe, modulos and recent work of Farg and Schultz, this is, but you'll see that this, critically, the global movement of legs of broad space of curve here. So this is actually really fabulous. So this, people talk about the mystery of F1 and why it's such an urgent question of what it is. This is why. So
I guess the idea is you could do something like CP tensor CP over F1 or something.
yes, that's right, because this is the space of untils, or it's supposed to be the, nice.
Sorry, one other question.
Yes.
For the arithmetically challenged, this multiplicity one thing, you're saying G is GLN, the eigenspaces are one dimensional.
I think so, though I'm not 100% sure. That was my reading between the lines. I haven't seen that written down, but I think so, because I'm pretty sure that must be a consequence of this, that the Hecke IG functions are each one-dimensional spaces, but you have higher multiplicity. And in fact, there are these Blasius and Larson show that it's actually the case that you will get global Langlands parameters that are not distinguished by Hecke, by the Hecke action. So there are some papers that are cited in also the forums
For general G.
For general G. Of course, for GLN, this is kind of fun. I should mention this. GLN, of course, this is just a standard representation theory. This function here, if I were to have a map from G to GLN, that's just a representation of GLN, and the representation of GLN is determined by its character. So in particular, it's certainly determined by where it lands in G mod G. So for GLN, there's something kind of special going on. Again, in this whole process, there were some very elementary ideas that I hadn't fully grasped that I can understand. So this is actually kind of fascinating. All right, any other questions about the global Langlands correspondences? All right, perfect. Now, 1, 2, okay, so I'm on this book. Yes. Yes, well, okay. If not, thank God it's recorded. All right, so now we're going to do a very, very fast blitz of geometric Satake. In the specific form in which it shows up, because the full factorizable geometric Satake is what's used by most. And of course, this is about Shtukas, so I haven't described the magical object yet. All right, here it is. So, all right. So, call that if D is a formal disk, D star is the punctured disk. Punctured dot there. And we have G prime, G torsors over D. And I'm now truly killing this chalk and burning through. All right, so hurt my hand. G sources over DG, such and phi is an isomorphism of the restriction of G over the punctured disk. This is what's called a modification. And the data of the modification, the measurement of this modification, called modification. The data modification, which is a generic isomorphism but punctured at a point, gives rise to a coweight of G. And the way that that works, though we've seen it again, it bears reviewing. It's that G torsors are parameterized by, well, if you look at those, yeah, this is going to be basically parameterized by GO, mod GF, again, V, so all local, mod GOV. And this right here is equal to the coweight lattice under the standardized isomorphisms that we've seen. So dominant coweight, sorry, yes, mod W, which is the same thing as dominant coweight. Yes, very, very important. Thank you. Thank you. So this uniquely determines a dominant coheot, which is also the same thing as a representation irrep of the dual group. Of course, geometric Satake makes great shows that that's not just sort of happenstantial combinatorial correspondence, but this really has meat. And so I'm going to very, very quickly describe the fully factorized version that we will require. So, okay, so I'm going to introduce the stack of partitions. This is called also a Hecke modification of modifications. Okay. So let I be a finite set. The great tragedy for this talk is if it gets subsumed in the horrifying C, that is factorizations and setting up factorization algebra. If that happens and people lose me because of that, I have failed as a speaker. So this is the great word. This is one of the few times I write this out very explicitly, and hopefully it will then be comprehensible and will take all day. So be a finite set. The partition IK. Okay. So let W be an irrep of G hat to the I. Okay. Now remember, irreps of G of powers of G are given by external tensor products of irreps of G hat. So we can write it like this. Each I, there is a corresponding dominant coweight, which is the highest weighted that representation. Now, given a collection Xi, given a point of basically the power of the curve, valued in some rating R, we write X times R hat for the formal completion of the divisor, the graph of the divisors Xi contained in spec R times X. we're going to define the stack MIX with some declarations of partition at the top. W R classifies the data of a finite collection of points of X and X by I, the point and R point of Xi and R. G naught through GK, G torsors over X times R's formal completion. So each one's defined over the full completion. And then for each, we have these maps phi j, which are maps Gj minus 1, restricted to X R. Okay, I'll have to write this map vertically. Forgive me for this. J, X R. So we consider the sort of puncture of this formal completion, and what we have is an isomorphism over each punctured sort of formal completion of each punctured formal disk, where the isomorphism is defined away from the xi for the I in ij. And so here we have j is going from 1 through k. And such that the modification of phi j at each xi for I and ij is less than or equal to lambda I, the dominant coweight of Wi, the representation. So I'll put a big bracket on all of that. I hope that that's visible. So what does it give us? We have a whole bunch of punctured disks. It parameterizes a whole bunch of formal disks. We have G torsors over the lot of them. We have isomorphisms on the punctures of them given by the partitions. And so, yeah, so I think this is combinatorially correct. So I hope that this actually makes sense. This is the stack over which we will.
What are the lambda i's?
The lambda i's come from the representations. This representation W, yeah, so I can say I is a finite set, and W is a rep of G hat to the I. It's an irrep actually.
And is there a full map to the BD-Grassmannian?
Actually, the map goes in the other way. This is a quotient of the BD-Grassmannian by a group, actually. The group of global sections of X times R hat. Yeah, so this group.
Like GMO at these points.
Yeah, GMO written in this very fancy.
This is it's like the Hecke stack. It's like a decorated version of the Hecke stack, which is like the Grassmannian not GMO, right?
Yes.
But here is this W means you're looking really at like a sugar variety inside of it and not the entire thing.
Yes, and I should also mention there is a composition map from this to what we would, if we don't put the partition on top, that's presumed to be the same as just the full partition is just the set I. So if I write just M sub IXW without the subscript, and there is a map from this to forgetting the partition. Yeah, so I mean, so yeah, it also is functorial with respect to W, I'll write that in a second. But there is a map from this just to MIXW, and then partition is just all of I, given by, well, each of these is generically trivialized, so they're all on some puncture. So there, it's certainly defined. Each of the GIs are certainly, each of the phi i's are certainly defined over the puncture of all, removing all of the xi. So you just compose all. So this is a sort of, this partitions the generic, in the standard Hecke stack, which only considers two G-torsors and a sort of, and some, you know, some sort of generic isomorphism between them. This one considers a whole sequence of G-torsors, G1, Gi, G. Should actually write this. Doesn't think this might make better sense. Sorry. Sometimes being precise actually harms the harms the intuitive meaning. So this is
also sometimes called the iterated Hecke stack. Right?
iterated Hecke stack. That's so good. Okay, I started calling it in my emails to Professor Drinfeld the partition Hecke stack, and he responded using the same term, so I thought it stuck. But this is
We'll talk about,
basically
like, iterated.
parameterizing. Exactly. That's why I have to sort of at least once mention this to GK, and this is 5K. Yeah. Right. And these are all generic. So it gives a whole sequence of these G-torsors. These are all generic trivializations. These are all over punctures. So over the largest puncture, you remove all the points characterized by I. You can compose these maps, and this gives you a map to the standard what we call Hecke stack.
If W is trivial, can you say what this looks?
So if W is trivial, that basically means that there are no modifications whatsoever. So these are just a string of isomorphisms. So this is just BunG, right? These are each one gets identified as part of the data with every subsequent one globally, right? And so that's actually a very important observation, because that's where this, you know, it's the I is empty case that actually von Lafforgue is studying, that we're studying the Langlands correspondences. So yes, the W's are telling you how far apart each of these can be, and in this case, there's some kind of order. So it's all right.
Sorry, you said that if I is in the empty sector, you would get BunG, is that?
Oh, I'm sorry. No, I'm quite wrong. What we would get is probably the yeah. In this case, sorry. So yeah, sorry. This is what you would get if these were empty. You would certainly identify them all over this. It would just be it would be it would be parameterizing G-torsors over a single puncture, over n punctures, right? It would be BunG to the, it would be BunG over d BunG d to the power of I. Yeah, right. I think that would be it, right? So sorry, yes, you're quite right. So this is in the standard Hecke stack setting, which you see usually when describing Satake. This is, yeah, but this is only done over each puncture disk, right? They're not globally defined curve. Yes, thank you. That's a very good point.
Wait, so for W trivial, that's
it's not BunG X, it's BunG D to the power of, yeah, it's BunG D. Yeah.
But the W is, it's kind of a weird notation, right? Because you're really like, it's just determined by a map from like I to the dominant coweights, right? It's like the combinatorial thing. And it's exactly like telling you, if you ignore W, this is like this in stack, and this is like just cutting out some closed substack. So as you go over all the dominant coweights or all maps from I to dominant coweights, you get the full thing.
Yeah. And so now, just very last thing before geometric Satake, and I'm not going to write out everything because your eyes will melt and it's hard enough to just parse this data. But what it does is it associates the map W mapping to this reverse sheaf. So these, you can consider the inductive limit as we increase W with respect to the standard order on the coweights. And that gives us a big stack, which you might just write as M sub IX. And these are all strata of MIX. So these, you can consider the intersection cohomology sheaves on each of these individual strata living within the big stack. So what geometric Satake says is that those perverse sheaves IW, I1. Again, this is the fancy version, fortunately. It would be nice. In my notes, you'll see it's built up. So extends to a tensor functor. A naught rep G hat I. Again, this is for arbitrary I. That's the extra thing that this is giving us. The standard geometric Satake is I is the one element set to perverse sheaves on this iterated Hecke stack or partitioned Hecke stack. And this is the really important thing, compatible with factorization. So compatible, I'm not going to say what that means, but if I have a function from I to j, the natural maps that you can imagine pulling and pushing these sheaves along those maps, and the natural structures we would transfer from, a representation of gi to g to j, g to the j, all of this sort of commutes. So I'm just going to say, that this is factorizable, and I'm going to leave that as a combinatorial black box you can imagine if you like. So this is very important. And in the cases that we need, we will delve into it. Now, I know that we're nearing the usual breakpoint, but I cannot let you go to break without defining Shtukas. Otherwise I get failed. So, Shtuka time. Okay. So, I think it'll be psychologically helpful. I'm going to write down the definition of the good old-fashioned Hecke stack with respect to W. So this is with respect to an arbitrary power of the curve, but this right here. So, the stack. I'm trying to minimize the number of times I have to write down functors of points like this, but you have to sometimes define terms in math. So, alas, equals set of xi, I is xi, the r, g and g prime, just two, not a whole sequence. Fine, just a single nice guy from the curve minus the graphs. G prime. Such that in the phi bounded dominant cohomology of Wi. Okay, so that's the good old-fashioned standard Hecke stack, at least in the power of the curve.
So it's X, but it's actually X cross.
Yes, sorry, I'm going to put little R's in scripts here. Thank you very much. Yeah, that's what type check is. This is XR, and we're considering the complement of X times R of the graph.
So also the previous.
And yes, thank you. And yes, so now this is the global thing. And again, if W is trivial here, you're forming an isomorphism between the two. So this is genuinely BunG.
Just an additional question, why did you write W as a script?
I'm so sorry. I put W wherever there's space to fit it in my notes. I'll try to sort this out. Trust me, the original Lafforgue has N as well. But I stick W wherever you can. Same thing with et for a tall. You stick it wherever you can. So this is the Hecke stack. This is again not related. So now we come to So forgive me. I needed to introduce that. I think it also helps put that in perspective. The difference between these two cases is that's only defined, each G is only defined over a formal disk, and in this case it's defined globally on the curve. And so now we say the stack Shtuka, and I think it's I, X, probably W goes on top. I Shtuka W, let's do I W here. I can check my notes, but and so forgive me, the decorations may go all over the place. Is the Cartesian product BunG to BunG times BunG Hecke stack fiber product goes like this. Is this correct? Okay, good. So that right there is the category of Shtukas. So it is the fiber product of BunG. Oh, I have this.
I want a different notation for the upper one.
Yeah, that is the stack of Shtukas. Sorry, that's not Hecke stack. So the stack of Shtukas is the fiber product of the Hecke stack with this map from BunG to BunG times BunG. That's a very concise way of putting it. And so more formally, more concretely rather, now this gives us a pair. This right here means that the two G torsors are going to be identified with one another up to a Frobenius twist. And this right here means they're generically identified with one another. So in this case, I'm just going to call them G and G. So I'm not going to write this out. So what this actually classifies as G is, well, it's classifies Xi, a finite point, finite number of points of XIR. It classifies a G torsor G. I'm just going to use one for this case. In theory, it should be two, but over X. And it classifies the data phi of an isomorphism from G to X and I probably over X bar minus, thank you. That would be nice. That. Go. So it gives us an isomorphism. So yes, what is the pullback of one comma from R over X? This is when we consider this is a G torsor over X times R, right? Over X times spec R. So I'm going to pull back along Frobenius on R and the identity on X. And so what this does is it gives me a generic isomorphism defined everywhere away from a finite set of points of G with some kind of Frobenius twist of G. So that is what the stack of Shtukas are, and very explicitly written here. So a couple of points.
Wait, so in the Hecke stack, you require specifying two G torsors, but here it's just one.
Yes, and the reason I'm doing this is that so this right here will basically, this map here will identify the two G torsors that I have with one another, right? So I'm collapsing it a little bit to just one G. So in this case, it's a map between G and G. The way if I were to write this out really precisely, say there'd be two G torsors, G and G prime, a generic isomorphism between them, but then an isomorphism from G prime to the pullback of one comma frog of G. So I'm just composing those and forgetting the middle structure in this case. So right. Okay, so a couple of points about this wonderful. So this is a Deligne-Mumford stack. Now that's interesting because of course BunG, this was surprising to me at first, BunG is an Artin stack, so what gives? Well, the answer is when you insist upon this Frobenius pullback isomorphism structure, you're basically taking only rational points, the automorphisms. And so this will look, if point mod G is an Artin stack, this will look more like point mod GFQ, where FQ is just a finite group, finite set of rational points. So this is actually has finite stabilizers of every point. I won't explain that. And there's a map from Shtuka I W through the Hecke stack I W to my stack of modifications I W. Again, W's decorations are moving up and down as I willy-nilly. And I'm going to call this map, and what the map from here to here is I just trivialize again, remember, when I say there's no subscript, that just means the partition is all of I. So in that case, I'll just have two G torsors, G0 and G1, and then a single isomorph is defined away from the graphs of these. Then it'll just be restricted to the formal disks of each point in the puncture. And this map here, we're going to call U. This is not canonical notation. I just needed it. And this, I think, is canonical notation, by which I mean one sum of the form uses it, which is P. But unfortunately, it does not mean the map from P to BunG, but P fractor, which is the map from Shtukas to X to the I. Now, oh, very, very important term. And I will probably, I think. Yes. Okay. Yes, I'll say one more thing, and then I'll say two more things, and then we'll have a break. So the set of this set of Xi are called the legs. So this is a very important term. So if the set I has n elements, this is called the stack of Shtukas with n legs. For a particular R, it would be R Shtuka with n legs. So in this case, the map P only remembers the legs. And just an aside, I asked Professor Drinfeld why it was called legs. And he informed me that it was not his terminology, it was probably the wrong Lafforgue's terminology. And he told me that at a conference, he on Vincent Lafforgue's work, so shortly after he announced his big proof of the conjecture, Conjue, his student, had a stuffed animal. And the stuffed animal was a very interesting, curious-looking beast. And again, all this was encountered to me by Professor Drinfeld. And he asked her what it was, and she responded in French. En Shtuka au mille pattes. So in French, the word for leg is paw, which translates to paw. So these are paws or legs. And that means a Shtuka with 1,000 legs. And Drinfeld was a little bit, he liked this, but he thought that was unlikely to be the manufacturer's original intention. So he asked what the manufacturer's original intention was. And it turned out to be a so-called cat bus. And so I had to look this up. He said he didn't know what it was either. The cat bus is a character in Miyazaki's film, My Neighbor Totoro. And so he told me the cat bus is the key image here. So you want to understand the legs of the Shtuka, you've got to imagine the cat bus. So that's a little diversionary thing. So I think that's yes. And he said there are two reasons for it's being so fundamental to this story. One is it's good to people, and two is it has 12 legs. So it's not quite 1,000, but all right. So the very last thing I'll mention is yeah. So now just before we go. That's a fun little diversion, but I do want to mention one more thing, which is, of course, the stack of Shtukas comes with exactly the partitions. It comes with their partition analogs that you see in the Hecke stack, and in particular, it comes with stratifications that come from these. The W stratify this big stack of Shtukas, and that each W is a stratum of this big stack. So it's saying yes. So yes, let me actually see it where I obviously did put that somewhere. Yeah. So that's actually clearly right there. Just in small enough text that I was about to miss it. So yeah, okay. So what happens if we consider Shtukas with no legs? Okay, well, so firstly, if there are no legs, the only strata we can think about are representations of the 0th power of the dual group. And the 0th power of the group is just the trivial, there's only the trivial representations. This has to be trivial representations. So what does that mean? That means that I have an identification of G with one pullback Frobenius of G with over the entire curve. No legs. So what does that give us? That gives a rational point of BunG. So this is. And by this, I really do mean the groupoid consisting of the FP points of BunG. So this is a Deligne, again, this is Deligne upward stacks. This is point mod some finite group of the kind whose mass we measured last quarter, the Tamagawa. So that right there is the Shtuka with no legs. And
which Frobenius? are you using?
Great question. Answer is relative Frobenius over FQ. Yeah, I tried to R over FQ. Yeah.
Which write up the relative Frobenius, please. Thank you.
Oh, you want me to? Oh, okay. Okay. So yes. So this is the one that is an FQ map. So this is the one that this one. So it doesn't act on the field of coefficients. So it's the one that takes the coefficients and takes their P power. Do I want? Yes, I want Q. I want Q. Sorry. Yeah, it's not. So it's just raising to the Q power thing. Yes. So, but yes. So if I so yes, I should be a little careful. I might tread the hot water. Yes, this is yeah. So this is just raising the slave.
And then when you base change the algebra through those.
Yes. Okay. Yeah. I don't think I'm gonna have that problem because it's all valued on FQ algebra. So okay. I mean, Tom, if it comes to the point where I potentially mess up the Frobenius, we'll take a look. We'll inspect slightly further. But yes, that's a great question. And I did double check. I Googled that and made sure of everything. So and the very last thing I'll mention is now the following, which is basically the heuristic is that the intersection cohomology of the stack of Shtukas, sort of bounded by data W, just as it was for geometric Satake, those perverse sheaves that were generated by the corresponding strata, the cohomology of these give the automorphic spaces sought for by Langlands. So in particular, these are like Schindler varieties, although I know very little about Schindler varieties. Professor Drinfeld warned me against saying too much about them. But these exist for arbitrary cohomologies, not just minuscule weights. And part of the original inspiration for Shtukas was this moduli space of Drinfeld modules, which are analogous to elliptic curves. And those are a kind of Schindler variety. So there's a connection here. So this is like in characteristic P though in the function field setting, characteristic P, it's actually nicer. With that, I will be more formal about what this means in the second half, and we then proceed to the proof. Thank you so much. 10 for it. Where am I? So yes, so I now need to make good on what this means. So here it goes. So what we're going to do is we're going to consider, and having written down carefully on this board over here, the enhanced partition geometric Satake, we're going to define a sheaf. So I'm going to take the perverse sheaf given to us by geometric Satake on the Hecke stack, pull it back to the stack of Shtukas, and then I'm going to put it forward to the lengths to x to the power of I on x to the power of I. So I'm being slightly cavalier here. If we really wanted to define this properly, and I'm not sure how much this technology now can exist in ensemble forms today, there are different papers that make it progressively easier to read. And so I think this, you may have to be a little bit more careful than I'm saying. You may have to, take some sort of limit, over a single dominant character bounding. There may be some up to indification. This is correct, but I'm pretty sure that this is actually just. And the other point is I just want to mention that as a matter of geometry, the singularities of the Shtuka and the singularities of the Valence and Drinfeld Grassmannian this patient stack, all which are sort of relative to one another. They're really essentially the same. And this is the point Drinfeld wanted me to emphasize. So this is really measuring the singularity of the stack of Shtukas, written in terms of pulling it back from the Hecke stack. All right. First things first. We're now going to study some of the properties of this. One, this stack is acted on by the global Hecke. Sorry, this sheaf is acted on by the global Hecke. And why is that? Well, the global Hecke algebra acts on these guys, so it filters through by transfer of structure to this sheaf on X to the I. By which I mean, for every X in the curve and B for G hat TVX, there is a corresponding morphism of sheaves acting on my. I haven't stated what this should be called. One problem that you're always going to have in this is there you can never have too many different variants of the letter H. H for Hecke, H for homology, and then all the different things. This one's going to be an ultra curly H, which I'm going to do like this, IW. Okay, so that's really curly H IW. And two, it turns out HIW is locally constant. Okay, so let's try to unpack what that means heuristically. Firstly, that will mean that there's hidden in this, when we go back to a geometric point lying above the generic point, there's going to be a Galois action. And that's the critical thing from our perspective. That's what we're going to be making. Yes, we're going to put, that's the purpose to which we will put these HIWs in the sheet. But just quickly, sort of heuristically, and this is something again I discussed with Drinfeld in great detail. You might imagine, why would this be locally constant? Why would it look like this? Because really, the data of this map, like the fibers over a given set of legs, don't really pay attention to the position of the legs. And so in some sense, you can imagine that this map here, this map P is, or is P from Shtukas W to XI, really is kind of locally async. But that intuition is not quite right because the fibers are not proper. And so in the original work of Professor Drinfeld and Lafforgue, they had to compactify the stack of Shtukas relatively. And then they had to be very sensitive about to make sure that the fiber at infinity didn't change. So the intuition here is not entirely correct, but you can sort of see that it really, this isn't really paying attention to where the legs are. The fibers are always going to be more or less given by these kinds of by these sorts of Schubert cell type stratification within the valence Drinfeld affine correspondence. So it's at least plausible. And in fact, this is a hard theorem to prove. It does take some time. So this implies, though, that HIW restricted to the generic point of algebraic closure of the generic of the function of the generic point is a pi1 x to the I theta to the I representation.
Sorry, you say the stack Shtuka is reductive?
No, definitely not. Locally acyclic means it's a constant vibration. Yeah, sorry, I didn't know that term too. I don't know quite why that's, does seem, someone says locally acyclic, that should mean it's contracted, like, I'm more,
It's locally acyclic along the base.
okay, sure.
Say.
Okay.
I think the striking thing about it is like it has this property kind of when the like collide, right? Like it's very believable over kind of individual strata, but the thing that's interesting is right.
Sure. No, that's a very
is also as
That's a very good point. Yeah, no, so yeah, what distinguished open set could there be? It would have to be when the points could coincide. So yeah, of course, the force behind all of this is a kind of stratified semi-smallness argument that is listed below in the geometric Satake. So this all comes, it all comes from it's also pulled back from geometric Satake in some sense. But yeah, this argument here. So now observe that this means that this particular vector space is a pi1 x to the I representation. Now, if you're not careful, like me, you'd immediately say, oh, therefore it's a pi1 of x to the power of I automorphism. But that's false. And this is a very interesting subtlety in the argument. Pi1 of x to the I does not equal pi1 of x to the I. So pi1s etols don't commute with products under two circumstances. One is when the curve of the space is proper. That's fine, x is proper in the unramified setting. It's not a problem. The other is when the base field is not algebraically closed. Unfortunately, FQ is not algebraically closed. So in order to get a pi1x to the I action, and the pi1x is the Galois side of things that we're interested in, you have to actually use a rather subtle argument, which is due to this lemma of Drinfeld, and apparently he was aware of this as far back as 1978. It's ancient at this point. It's very, I don't quite know the original motivation, but this is this, you'll see this word floating around about partial Frobenian. And the partial Frobenian will give us this. But there's a second obstruction too, which is that this sheaf isn't really constructible so much as inconstructible. And so now comes the point which may, in the work of AGKRRV, be surpassed, and that we can push and pull these things without any problem in this brave new world. But for von Lafforgue, this is where he restricts the so-called Hecke finite portion of this vector space. And so we're going to have to introduce that, and then I'll introduce the partial Frobenian. And so this right here is what gives us an actually inconstructible space. So am I? No, I have one more board here. Right? So sections of the sheet will be called Hecke finite if and I'm just going to at this point restrict to the generic point. Are those vectors in the vector space those vectors belonging to a finite generated CL module, finitely generated ZL module, stable under all Hecke operators. Okay, so this at first looks like maybe just a technical consideration, but in fact, it turns out to have real geometric meaning. This is the same thing as a cuspidality constraint. So there are sort of natural push constant term functors which annihilate the Hecke finite vectors. I'm not going to go into the definition of this, but this is due to conjugate. And conjugate in the same paper also proved, so now we're going to definition.
His name
Sorry, go
correctly.
ahead.
I'm going to pronounce his name, Tong Shui.
Oh, thank you. Song Shui.
If you want a more standard, better pronunciation in Chinese, it's Tong Xue.
Song
But I doubt
Shui. How is that? Song Shui.
Initial C is like a TS.
pretty close.
Okay. So Griffin, you and I will have to practice. I do apologize to you. This is the same Song Shui of cat bus fame. So this is a very important result here. So we're going to define that all important spaces, Greek, Roman letter H, no curlies, IW is going to be this IW. But we're going to restrict to.
Aaron, we mean it with love. The first time I gave a talk about the work of a no, I pronounced her name Helen as no. So don't worry about it.
Okay. Yes, it's only been recent that I stopped calling it Esnaut. So Esnaut. Yeah. So
And Tom, I learned this from you too, actually.
it was for talk in this seminar. So alas, we apologize. BunG seminar apologizes to all the myriad names we have botched from France, China, and elsewhere. We're going to define, we're going to define the HI vector space, and this is the most important structure for us, as the restriction of this curly H sheaf, this push board, to the diagonal embedding of the generic point of the curve. Okay, it turns out that makes no difference. There's a specialization map, and it turns out to be an isomorphism. Again, that's actually a difficult theorem that Lafforgue takes some time to prove, but we're not going to go over that. And then we're going to consider only the Hecke finite vectors. Okay. So that is the space that we're studying. And it turns out, this is also proven by Tong Shui, that this is actually finite dimensional. Which is pretty marvelous, actually. And again, let's talk about the special case of no legs whatsoever. This is exactly the space whose decomposition I promised at the beginning. Yes, so this you can see that this cuspidality holds more broadly, more generally for all I's and W's, but in this case, it is literally the cuspidal space of cuspidal space on BunG and BunG. So we know that it has a global Hecke action. These also, of course, by definition, have a global Hecke action. They're defined in terms of the global Hecke action having a specific, they're defined by being stable under the global Hecke action, finite. Most important thing about these HI Fs is that the Galois group F bar over F acts on the HI. So again, that more or less follows because of the reason I said here, it's locally constant, restraint. But we have to deal with this x to the I issue. So let's see here. Now comes the judgment call question. I could do this and it would take probably 10 minutes, but that runs to 540. And then I have two very long things to write out, which are the properties of the HIs and the excursion operators. So should we skip this? Do people like to skip the partial Frobenius idea, or would you like to see it? I'm going to leave it up to democracy here. At the risk of going over time, should we do the partial Frobenius, or should I leave it to questions? What judgment call? Any desires? Okay, so yes, modulo, being able to do algebraic geometry, characteristic P and non-closed out algebraic closed fields, there is this Galois action, which I know. So the actual proof involves these wonderful partial Frobenius and Drinfeld, and that was why we had to introduce the partition. You'd have to introduce the partition Shtukas stack, or the iterated Shtukas stack, Question.
Wait, sorry, is the Galois to the I or
Thank you. Oh my gosh, yes, absolutely it is. Yes, that's very important. And by the way, I just want to say, I'm not used to seeing this many groups to a power. This is something that was new for me, and I'd not really seen it before working on this, and so this like opened up a whole new vista of whoever knew you could do that without, getting on trivial stuff. So, okay, so I'm gonna skip over that.
Sorry, just one thing I'm confused about. You did this specialization to the diagonal thing though,
Yeah, that's subtle. That's subtle, and I won't be able to demonstrate
but
it.
nonetheless. Retain the action.
Yeah, in fact, it's sometimes when you do that, it's more obvious that the action works. But you do need to check that it's the same thing.
It's sort of, I mean, I guess we should think like this script H is secretly like a box product of things, right? And then you're sort of just tensoring them as vector spaces or something. It's kind of
Yes. No, yeah. No, exactly right. So that's actually yeah. Drinfeld also, you'll see this in the notes, gave me an exercise to do, which he said persuade you well, hopefully when they're all written up, that this will make better sense. But any questions? We have bought ourselves some time now, so.
I have one more. Sorry, just a very basic question. So is this hospital automorphic forms? Is it finite dimensional?
Yes, it is. And in fact, that's known independently. In fact, this equality can be done without the work of Shtukas. And Vincent Lafforgue did it himself just by hand because his work preceded by 5 years, I think, the full result of this one.
That's not up there. Any BunG and use infinite.
Yeah, no, it's not. That is a computation. I think, yeah, you can find it in the certainly in. I think you can find it. So there's a 30-page paper. So there's a 30-page paper, a 60-page paper, and a 202-page paper. So you can certainly find this one, I think, in the 60-page. I have not read the 202-page paper except its reference. So the 30-page paper is the most slick because it uses more modern stuff. Describes the Drinfeld heuristic at the end. So, but if you want the ideas, the 30-page paper is the way to go. Okay, so all right. So now let's get right to it. So these HIs are just bewilderingly structured. There are so many fabulous structures to them, and so I'm just going to list them. And most of these structures follow from the geometric syntopy downstairs, except for the Galois action, which requires careful study of these partial remaining centers. So first property A is that yes, for all finite sets I, the functor W mapping to H on W, and again. For U mapping W to W prime, we call it HU, mapping the corresponding HIWs to HIW prime. Problem of having to write the prime is the most important thing. Extends again. A priori, I've only really defined these on, well, I've defined them for arbitrary representations by a geometric Satake, but if you just trace through definitions in terms of IC sheaves, they're only defined for irreducible representations. So this extends to a tensor functor. From A naught of rep G at I. Rep gal FR with F. That's the first. This is the letters here are important because they become canonical, I think. They're A, B, and C. So this is A. Now we have property B.
You don't want K0.
No, I don't, it doesn't have K0 on both sides. I probably want, I want K0 on both sides, right?
No,
Oh, it's a functor. Ah, it's a tensor functor. So it's quite right, sorry, that turns into, yeah, sorry. Thank you. Yeah, I've been using in my notes those two essentially indistinguishable, so they can make you. So yes, now for all, and this is the standard letter now, zeta having defined it. I'm having finite sets. Now I'm gonna have to write out sort of factorization. We possess, we have isomorphisms C, so zeta, I'm gonna put the W as well to remember, from HIW to HI to HJ, W zeta, where W zeta represents vector space. So W. And again, for this to be meaningful, this has to be acted on by G hat to the J. So G hat to the J maps by precomposition with G I maps to N W. And this notation I'll use frequently. Such that now we have the structures on these seats. So yes, so we now have a map. So this is an isomorphism. So if I have any finite map of sets, this will actually produce an isomorphism. And these can be quite extraordinary because these are the fusion isomorphisms here. So we give a brief example of this at the end of this. So now we have B1. We have the obvious compatibility. So we have the obvious compatibility with respect to the maps HU, B1. We have the compatibility of these maps with respect to the Galois action. Variant. Now, of course, Galois of the power of J clearly acts on this side. We're going to make it act on this side via it's acted on by Galois power of I. And this is mapped to by Galois of F bar over F to the power of J, just by decomposition with map zeta. By use of notation. So therefore, this inherits an action of Galois power F to the power of F hat. And this isomorphism between these two is Galois to the power of J equivariant. 3. This one's nice to write out. We have 2 zeta and eta, then it's also compatible with composition. And then we have lastly C, which is the final property of most importance, which we already discussed, which is the vacuum module, identification of the vacuum module with the space of cosmology. So I'm just going to pause for a moment because I want everyone to sort of internalize this, because this is the thing that Drinfeld came to and re-axiomatized. So he wrote an email to Professor AGKRRV in 2013, which he shared with me, where he said, let's just call this data A through C, and let's look at A and B, forget C for the moment, and let's see if we can axiomatize the sort of Lafforgue data, and he expressed it in terms of another category, and we're going to come to that at the very, very end of today's talk. So these are the structures that these HIWs possess. So far, though, I'm not answering the question of how I can get Langlands decomposition. I've said that I would get excursion, give you this notion of excursion operators, and I haven't gotten them. So that's what we're going to use these HIJs to write down. Any questions on this, though?
That's not right. This is now from a while back, but I think something. When you say this, so this is associated to this space of present, all of these are dependent on the W.
Right. Yeah. So it appears a priori only to care about the highest cohomology, right, which gives you the bounds on the. So it appears to be very little data that's being used, but within these isomorphisms, the full package of factorization geometric Satake will appear. And so yes, I actually had, this is again a question so it looks very, HIW is defined, objects are defined in a very straight way. Yeah, so it all comes, yeah, so the full power of the tensor structure of these characters really comes when you start considering the package of the whole categories. So what we're going to try to think about is how to, Drinfeld thought about was, how do we reinterpret the category that of data that for every W, HIW, as we vary the odds. So that's what he finds actually can get naturally reinterpreted as the stack of coherent sheaves on the coherent sheaves on the stack of Langlands parameters. So we'll get there. But I need to first define excursion operators and prove Langlands. Okay. Excursion operators. So these are called excursion operators. I don't have a fun story for this one. It's literally written out in Lafforgue's work because they move the legs. So excursions, you imagine the cat bus walking. That's what you got to imagine this. So these are operators on which we see is by C is just the cosmology space. Sorry, I'm going to briefly. Two things need to be said. The first things first is that as exercise, just to sort of get yourself acquainted. The map from the empty set to the set of one element induces an isomorphism by this from the vacuum module to the Shtukas with one leg, where we're bounding everything by the triple representation. So that's an isomorphism. So the slogan here is one inert leg is the same thing as no legs. And moreover, if you take H 1, 2, and this is probably a good further answers Professor Matthews' question. If we take 1, 2 with the box times, then there's this. Well, I'm going to write as the inverse of the map from. This is correct. To H of 0. The corresponding representation here, well, this is restricting to the diagonal action G of this box times, or G hat in this case. This is just the tensor product. So you can already see some non-trivial fusion action. So very important example. Okay. So in order to construct an excursion operator, we're going to go on a hunt for trivial representations that lie in higher tensor products of representations Wi. So let's say we have a representation W of G hat to be I. And again, diagonally, this is a direct representation. This is tensor product representation of representations of G hat. And let's look for, and these will exist eventually as you start tensor producting these things together, an X in W that is diagonally G invariant, G hat invariant. In other words, as I start tensoring WIs together, look for a sub-representation that's just trivial. These will come eventually, and likewise for dual. If you're confused about my board work, which might be a little bit poor at the moment, this is the data that's needed to set up an excursion. We need such an X, so if you can't find any such things, you're hosed. But you will be able to find them in general.
You're saying you might choose I some way, or it's for any.
Yeah, so no, so for it might not be true for all I. It's possible that the tensor product of two represent. This is the Plethiism problem, right? When I take a tensor product of lots and lots of representations, when is the trivial representation here? So excursion operators are somehow related to finding trivial representations in higher products of W's, which is very cool representation theory problem. Again, something I've not really thought about having sort of much, so that is. Okay, so search for. I'm going to say let, not best grammar on the board, but okay. Now here comes the excursion operators. Okay, so I'm going to use the fact mentioned here that one inert leg is the same thing as no leg. So we're going to start with this and make sure I don't get my inverses. So the function zeta will be the set of I to the trivial. That's the only function that we're going to use here. There's only one such function. This is logic category set. So what we're going to do is we're going to make this magnificent chain. So H0WI, HIW maps to and this is the longest board. So I'm sorry, I'm gonna have to, I can't feed this uneconomical. You have to get it in one line, or else it's just not visually good. W to HIW to H0 W zeta H. All right, so we're going to print this long chain of maps using these x's and these. So this is going to be right here, h of x, because x gives us a map from the trivial representation into W. This right here is going to be the factorization morphism from zeta I inverse. And likewise, this is going to be the factorization morphism I zeta I. Right, is this visible on the camera? Okay, good. I'm sorry, I'm caught between a rock and a hard place. I only have so much length on the board, and so I need to you can't be. And this right here is going to be an arbitrary collection of gammas in my Galois group. gamma I. So let's look at this. It's wonderful. This goes on here. We start with really with the vacuum module. This is the same thing as the module with one inert leg. Now we map that using the one inert leg. We map it into a trivial we look for a trivial factor in some tensor power. That gives us this map here. Now we map that into HIW by the canonical map given by the inverse of the canonical map given in this factorization. Now we move all the legs by this Galois action. Again, apply the canonical W, and then this right here is H eta. So H eta gives us a canonical map from the W tensor to trivial, or from W to trivial. Equivalently, it's a trivial subfactor of the So the way that Lafforgue describes this is this right here he calls the creation operator. This sort of chain of three he calls you have the legs all attached at the same generic point. Now you allow them to move differently under the action of the Galois group, and then you reattach them generically, and then you annihilate. And so this gives us a long chain, and then I guess there's the again it's canonicalized. This gives us a return to the vacuum module. So those are your excursion operators.
Question, I think this is like the true meaning of the word excursion, at least from what I remember hearing Vincent speak about it, it's like you start in this vacuum module and you go on a long excursion for all these other vector spaces.
Yeah, okay, that probably makes sense too. Yeah, I mean, and of course, in order to even set this up, you need to have done some hunting at the beginning, to find these trivial representations living in these higher tensor pathways. Just it's amazing. It's in these higher tensor products. So yeah, okay. So now there's a beautiful big algorithm shocking. And misplaced you. Okay, so that is this. So now, if we notice, we have here the data of X in WG hat and eta in W check G hat invariant, G hat acting diagonally in each case. These are a priori G hat to the I representations. So we actually have a matrix coefficient, eta paired with GI and G, I and I applied to X, right? Which is an element, okay? This is this guy's left, based on the invariances, the left and right invariances here. We see that this is an element of O of G hat, mod G hat to the I, mod G hat. Okay, so there, for every pair of these things, there exists a matrix coefficient. On this extraordinary space where we take a power of G and then mod out on either side by the diagonal action of G. Again, hats. My pants are collapsed right now. So this truly will be the last time I wear this tail coat. It served me well, but it's got one leg in the grave. And so it turns out that, so let's call this function f, which maps G hat. Well, okay, so this is actually really the GPT quotient. It's a function. It's partly O, this GIT quotient. So it's an invariant function in the algebraic sense to QL bar. Fact, and I won't prove it, but it's a nice argument. This excursion operator depends only on F. By the way, just as an aside, I did ask Richard how he thought of excursion operators, and he says, I don't. He's like, they're hard for me to think about, and that's why he had to reinterpret them into something nicer, which is what leads to the AGKRRV. So if you're confused by this amazing detour through all the other vector spaces, no worries. It can, properly trying to escape from the excursion operators can lead to beautiful things. So defining an F. So we're going to call this excursion operator, call it S I F gamma I.
So it also depends on. You're saying it doesn't depend on X and C.
Oh, yes, on F. Okay, thank you. Yes, on F and gamma I. But of course, yeah. So this is as opposed to the pair X, C.
Nor does it depend on.
Nor does it depend on double. That's right. Yeah, that's a very important. Yeah. So now I don't think I'll be able to write down all of the properties of the excursion operators. It will be a bit like writing down these. There's there actually are 5 properties. And I think now it's almost 6 p.m. And so I do want to let people go. So I won't write them all down. I'm just going to write down the 2 most important, which. Okay, so 1, the SIF, the S's commute. We call the set of them B. Okay, so call the set. This is the set of excursion operators. So they all commute. Okay. 2, and this is actually number 5, but this is the most important. The Hecke operator TVX for a place X is the same thing as the excursion operator with 2 legs, the function f that I'm about to define, and the map frog v, comma, and the function of Galois group frog v, comma 1, where perfect.
Aaron,
Yeah.
I have to go. Go. Thanks for the talk.
Thank you so much. Really
Yeah.
appreciate your coming.
Thank you.
I'll practice my
Yes, I see.
pronunciations.
Yeah, I see. Yeah.
Yeah, we're close, and I apologize for going over time here, but this is very important. So this right here, where now to tell what F is, where F. Again, this is a map from G hat mod G hat squared mod G hat to a base field. Well, bar is given by F of G1 comma G2 is the trace on V of G1 G2 integers. So a whole bunch of properties which show that these things commute and how and describe how composition really corresponds to multiplication of functions. And the most important constants are 1 is a commutative algebra, and 2 you can sort of recover the Hecke action through these functions. This is the hardest part to prove. He requires a geometric argument. This is this is sort of in some sense the central calculation of the paper. Okay, so this is what gives us. This is what allows us to recover through the action of the Hecke compatibility. Okay, so B obviously acts on CC cusp, so we can diagonalize.
Oh, I see it.
Yeah, B is the set of. I should have written that first, but I just said B is commutative, but my work was, in the rush to the end, getting a little bit poor. So B acts on the cuspal space, so we can diagonalize with respect to this action. So claim. By the way, this is defined as an algebraically closed field, so Shtukas applies here. Every character B, big B, keep it all bar, corresponds to a unique Langlands parameter. Okay, so briefly say why that is. So if I fix my gamma I and my I, this gives me a map from G hat mod G hat to the I mod G hat. To Q of R. Two. Okay, I can't erase. Unfortunately, everything on the board is important, so I can't really erase anything. But property A was the least important of those, so. This is it, and once we're done with this, I will end the talk here and leave maybe Drinfeld's reinterpretation to the questions. So thus, the gamma I gives us a map from the Galois group back over F R over F to the I to a point in G hat on G hat to the I on G hat. Right? Say I has n plus 1 elements, including 0. Observe, this is a very nice observation, that this double quotient is the same thing as G hat to the n mod G adjunct action. The map is G1 to Gn maps to 1 comma G1 Gn. And you can satisfy yourself that that is correct. So what we see, so what this gives us in the case of n equals 2 gives a map from, n equals 1. So where this is, but this is 2 elements is gives the map from Galois for F to G at mod G, which we're going to call, which is this Langlands parameter sigma. And what we find here is that B, and then the so in the case of sort of when I is very small, we get exactly Langlands parameter, and it shows that induces all the higher maps. And that comes from these extra properties, which I have not written down of the SIFs, which in turn come from the factorization properties of these HIWs. And so what we find is basically these all of these maps here are basically going to be in the form of sigma to the power of I for some map sigma of this. And so that's how you're going to argue. And then what we find is the sort of, let's call it the excursive compatibility as opposed to the Hecke compatibility, is that nu of SI F gamma I is F of sigma of gamma I all I. So this actually shows us that the decomposition with respect to B is parameterized by these characters of B. Each character B corresponds uniquely to a Langlands parameter. So buried in here, it's one thing, this uniqueness, the unicity property, and that actually comes from some sort of general properties of representations or variance powers of groups like this, which is due to Richardson. But that's actually quite a nice thing. It's not very difficult invariant theory or anything. But somehow, how does this solve the problem that we described at the beginning? If you have a map from gamma to G, it's not determined necessarily enough to conjugation. But if you really know all the higher powers as well, gamma I to G to the I, and you consider the corresponding map G to the I modded with G on both sides, that is sufficient to determine uniquely the original conjugacy class of the map from gamma to G. So in this is, I know it got a little bit rushed at the end, but this right here does allow us to complete the whole picture and show that the Langlands decomposition comes from this diagonalization of excursion operators. Now, one last thing, this does not give you the multiplicities. There's extra data in the Langlands correspondences, which are predictions that are made by the Langlands correspondences. This does not give you access to. In fact, in particular, we don't know if for any given Langlands parameter, the space is 0. So that's unfortunate, but compatibility with local Langlands, which is the other desideratum, actually was done in a separate work of Lafforgue, with I'm going to botch his name, but it's like Garestier or Garestier. Forgive me if I'm messing up the name, but so this is the centerpiece right here. So thank you so much. Want as a bonus track afterwards. People can go now. We can explain Drinfeld's reinterpretation. Unfortunately, I didn't have time to get to. Any questions?
So like this doesn't tell us, for example, I think maybe you're saying something like this. If for example, if I have a Langlands parameter that's non-cuspidal, I would expect that the corresponding component in the cuspidal forms vanishes, but I don't think that we know that for this, right? I mean, this just tells you, you have some decomposition over all possible Langlands parameters, but it's a priori you could get some non-cuspidal Langlands parameters appearing in the cuspidal forms, right?
So, we have some non. Yeah. Okay. So yes, one. Okay. So I have certainly not explained. Yeah, that should follow from the general theory of induction. I've certainly not explained why the sigma actually does not lie in any proper parallel. I have not given that as an answer. So yes, you're wrong. So I ought to really, for completeness to say, I think that is actually that must be covered by this work. I haven't spent that. I just mentioned this also. I feel that I gave this slightly short shrift. This factor, because of property 2 over there, does imply Hecke compatibility. It's just much stronger. Even this, as you can see, it's arbitrary from I2.
So I guess the reason I ask is because this is a thing that Sam claims in this like new paper where he has this arithmetic application AGKRRV. So I wasn't sure if that was something that could also be deduced from.
So yeah, the story of the induced forms and the sort of the nature of the sort of direct integral that you have to take, I'm not actually sure I know very. I just don't. I just don't know at all. But it should, I think, follow from the general principles of induction that you get the Langlands. So you just reduce it to a Langlands correspondence to Levi, and then you should be able to solve for cuspidal things with Levi. So whatever you do by cuspidal support. I don't know what verifications regarding the non-cuspidal characters Bonson did in his paper. Obviously, something must have been done, or else it wouldn't fully solve. I just don't know. Perhaps if there's appetite, I should just mention the one line sort of Drinfeld interpretation. I feel really bad because that's sort of and that's how do you understand these ABCs? And so what Drinfeld does is I'll erase this because I want the B and C at least. He says that, well, let C be the category of Lafforgue data. Because that satisfies A and B. And let D be the category of O modules on the stack Langlands parameters. It's when I know he called it C prime. And in the email, part of the reason I couldn't follow is he gives a functor from C prime to C, and I thought he was giving a functor from C to C prime. I'm like, he gives nothing. What is it anyway? It was a disaster reading it. So thank you to Kevin for explaining this to me. I sent him the answers like, please explain. So this is quite nice. So C.
Let's be clear what by the stack.
No. That is they're actually not supposed to be there. So it takes a lot to define in a way that's that.
I defined it in my talk in some abstract, which
Yeah, so I will say that there's a neat way to at least think about it, which is that C is maps from B gamma. Okay, and then also Drinfeld use gamma for Galois groups, sort of and G hat, remove the hat, it's just G, okay? BG. Okay, so there's so this is its category. And so the idea is, he produces a functor from D to C. So say n is an O module on the stack on let's call this. Sorry, that's not C. C is the stack of O modules. Let's call this stack Y. This is Drinfeld's notation. And let's call C the O modules. Okay, sure. Okay, so let n be an element of C.
Sorry, the two C's.
Oh,
C denoted the fourth data.
D. D is defined to be the O module. Sorry, thank you. Yes. Oh gosh, yes. The C is the fourth data.
Sorry, sorry, O of Y is the category.
Yes, this is O module.
You mean like quasi-coherent sheaf?
Yes, that's O should be O sub
That
Y.
just looks like functions.
Oh, bugger. Okay, so O mod. There we go. Now, okay, sorry. Here, data. So okay, so given n, an element of the category D, an O module on Y, I need to produce basically a correspondence. Every I and every W needs to give me a space HIW. And so the map is as follows. You consider the correspondence B gamma I times Y to the I. And you have a projection from this to B gamma I. You have a map from this, which we call evaluation, because this is maps from B gamma to BG to BG to the I. And I pull push with respect to the kernel N. And so the functor is defined as lower star of pi, the lower shriek of pi upper star of so we need an element of B, so W. Yeah, okay, so yes. So notice that I first messed this up here. So an element, a representation of G will be W is the same thing as an O module on BG. So an element of BGDI is the same thing as element of O module of BGDI. So now we're going to pull push this way. So what we're going to do is we're going to take the functor D to C given by W maps to Ev pullback, let W tensor M, and then we're going to do pi. So that will take a representation W of BGBI and produce from it sorry to all my terrible notation.
It's Kyler star, right?
Did I mess it up here? Oh no, you're right. I did get it right the first time. Sorry. Yeah, E gamma. That's right. Yeah. So this will take a representation W of GDI, sorry, pull push, and produce a representation of gamma I. So the question that Drinfeld asked is this functor?
It's Kyler star, right? There's no such thing as.
Oh yeah, of course you're right. So used to pulling and pushing locally constant things that I forget my six functors. Question: is this an equivalence? And so here's the answer to this question. We asked Sam Raskin equivalence from the C. The answer is this is what's called main conjecture 24.4 or 28.4.8. I wrote it down here 4.8.4. My first instinct is correct. 0.4 in AGKRRV. And it follows from geometric Langlands, and characteristic P. So this is not solved geometric Langlands characteristic 0, in part thanks to Kevin, is solved. But this is only solved, I think, for GLN. I think it's something like this. So this is not, this is, so certainly this is open still. But it would result from, there were some unconditional results that Gatesbury mentioned, sorry, Raskin mentioned, that are in Gatesbury, but the big main conjecture is still,
sorry, like with like characteristic coefficients. Personally.
I think so. I'm not, all I know from Raskin's message is, all I know from Raskin's message is it was just, this would follow from geometric characteristic P, so I'm not sure that what specific characteristic. So this is the state of the art. Sorry for all for this. This actually makes some sense. The category of O modules on the stack of Langlands parameters is very natural. Category of Forte is really complicated here, so it'd be nice to. That truly is all I. Oh, question.
How did you pick n? You're like you just pick an arbitrary n and then claim that this one.
That's right. So Lafforgue data means an arbitrary W gets an arbitrary is a correspondence from BGI to B gamma, right? An arbitrary W, which is a representation of GDI, must give us a representation of gamma of the I, namely HIW. So the point is that the n gives me the kernel by which I can establish this correspondence.
Oh.
So yes, again, do not worry. As you can see, my slide showing this took me a very long time. Kevin explained this to me very helpfully. After some panicked text messages. I asked Professor Drinfeld to re-explain it. He said this would be a good exercise for you. So thank God we got you. Justin said, all of you, thanks a lot.
Final